Hello, today we'll be talking about the derivation of PCA, as well as the method itself. PCA can be entirely derived based on a couple of motivating objectives. The first one is that PCA is trying to find directions in the data that preserve the most variance. The second one is that we want to try to pack maximal information in just a few dimensions. So that means the dimensions that we find themselves are not going to have redundant information or correlation. This is all under the assumption that we're looking for linear combinations of the original features as the directions. Given this, we can go ahead and set up an optimization. Recall that the variance of some variable v, which is written in terms of the original features, is v transpose times sigma, the data covariance matrix, times v. We can simply set up a maximization that says, let's maximize v so that this quantity right here, the variance, is maximized. But there's a way to cheat that optimization. Namely, we can just make the magnitude of v arbitrarily large by scaling the vector. But since we want to avoid that, we subject it to the constraint that v have unit norm. This kind of an optimization, where there is something that's being maximized, subject to a specific constraint, can be solved using the technique of Lagrange multipliers. Under the Lagrange multipliers technique, you have a function f of some variables that you're trying to maximize, and you have another function g, which is serving as a constraint, and here we need g to be constrained to equal 0. If that's the case, then you can solve a different function called the Lagrangian function. The Lagrangian function has an extra parameter called lambda, which is also called the Lagrange multiplier. And this new function is simply f minus lambda g. The reason this works has to do with the Lagrange multiplier theorem that says that any local maxima of f under equality constraints, the gradient of f can be expressed as a linear combination of the gradients of the constraint, which here we only have g, with the multiplier being the coefficient. To get a geometric idea of this, what we're actually trying to find is the maximum value of f. If it was unconstrained, it would be over here, but we're subjecting it to the constraint that g of x equals 0. So basically, at the point, optimum point, these two are tangent to each other, and so their derivatives are parallel but point in the opposite direction, which is why this is subtracted here. So given this, we can come up with a modified optimization. Here we're maximizing the variance subject to this multiplier times the constraint that v transpose v minus 1 equals 0. So now how do we actually solve this? Like your calculus class, you differentiate it and set the derivative equal to 0. If you set the derivative of this equal to 0, then what you have here is something like an x squared in matrix form. So you get a 2x times this constant here, and the same thing here. And 2 lambda times v, and then this is just a constant, so it goes away. If you divide both sides by v, you basically have it. You have the answer that what we need v to be is actually an eigenvector of sigma, because it has to satisfy sigma v equals lambda v. Moreover, it should be the eigenvector with the largest eigenvalue, because we want to maximize this. Thus, the v we're looking for is the eigenvector u sub 1, which has the largest eigenvalue. What about the other principal components? To obtain the next direction or the next vector, we maximize the same optimization, but with respect to the constraint that it's orthogonal to u sub 1. This gives us the second largest eigenvector u sub 2. Recall that eigenvectors are already orthogonal to each other. This means that when you project data onto them, the PC components will not contain redundant information and will be uncorrelated. This brings us to the PCA method. It involves first computing the data covariance matrix, eigendecomposing the matrix into eigenvectors and a diagonal matrix of eigenvalues. The loadings, or the linear combination of features, are found in U, and the new projected data, or the PC components, can be found by multiplying x by u to get the projected data called x tilde. There is another advantage to PCA besides giving you loadings and the new principal components. You can also tell how much exact variance is explained by each of these directions. Suppose U is a principal direction. Recall that the Rayleigh quotient gives the eigenvalue corresponding to this eigenvector. So if, instead of A, we substitute sigma, the matrix we're looking at, then we get a quantity like this. But remember that these are constrained to have unit norm, so you can just drop this term. So basically, what you're getting is that lambda, the eigenvalue, is actually equal to the variance. So the variance explained by any PCA dimension is equal to the corresponding eigenvalue.